College Algebra, Chapter 3, Section 5, Higher Degree Polynomial Functions and Graphs. A polynomial function of degree n in the variable x is a function defined by p of x equals a sub n x to the nth power plus a sub n minus 1 times x to the n minus 1 power, and so forth down to a sub 1 x to the first plus a sub 0, where each a sub I is real, a sub n is not equal to 0, and n is a whole number. In other words, we have this in descending order. We start with the highest power of x and work our way down. And the powers must be whole numbers in order for this to be a polynomial. A sub n is called the leading coefficient. It is the number in front of the x with the highest power. A sub n x to the n is called the dominating term. A sub 0 is called the constant term. And p of 0 equals a sub 0 is the y-intercept of the graph of p. In other words, when you put in 0 for x, what you're left with is a sub 0, and that is the y-intercept. Okay, we're going to talk a little bit more about some of these terms, repeat them a little bit, put them in a little more context here. The behavior of the graph of a polynomial function really is based on the value of the first coefficient and the parity, which refers to the evenness or oddness of that highest power of x. So because of this, a sub n, as we said before, is called the leading coefficient, and that whole first term, the a sub n x to the n, is called the dominating term because it pretty much determines what the graph is going to do. The term a sub 0, like we said before, is called the constant term and is the y value of the y-intercept. Also note that a polynomial function, unless stated otherwise, or if unless it's in an application problem, will have a domain of negative infinity to infinity. In other words, all real numbers. And the graph of a polynomial function is a smooth, continuous curve with no sharp corners. So there are no breaks in the graph and no corners. First of all, we're going to talk about a cubic function, and the cubic function is going to serve as our model for any odd degree polynomial. Cubic function looks like this. Its highest power is 3, and it must have that x to the third in there to be a cubic function. It will resemble one of the following shapes in general. Okay, it'll either be kind of that, still they both kind of have that S shape. One is a little more dramatic than the other, but generally this is what the function looks like. Then we're going to talk about quartic functions, which are kind of our model for even degree polynomials. And quartic functions are fourth degree, so they look something like this. And in general, they are going to have one of these shapes. Sometimes they look like parabolas. A lot of times they'll look like parabolas, but the turning point has widened out considerably. Now, this is a little different. What they're doing here with the dash is they're saying that this part can actually vary. A lot of times it'll look like kind of like a W, but whatever it does, it's going to be a smooth curve. It's not going to have corners or anything like that, but these will do different things sometimes, look a little weird. We've already talked a little bit about extrema, which are the maximum and minimums. They're also called turning points. They're where the graph of a function changes from increasing to decreasing or decreasing to increasing. It's where it changes direction. A local maximum point is the highest point or the peak in an interval. In other words, it's the highest point in the surrounding areas. Function values at these points are called local maxima. A local minimum will be the lowest point or valley in an interval. Again, it'll be the lowest point in the surrounding area, but not necessarily the lowest point over the entire graph. And these points are called local minima. Extrema, the plural of extremum, includes all local maximums, all local minima. Here's a little more about it. We've got a couple of graphs here. The one on the left would be an even power. The one on the right would be odd. And if you kind of study this chart on the left, P1 is a local maximum. P2 is also a local maximum, and P3 would be a local minimum. And then on the right, P1 will be the local maximum and P2 the local minimum. Now we also have what are called absolute extrema. And it says, let C be in the domain of P, then the following hold. P of C is an absolute maximum if P of C is greater than or equal to P of X for all X in the domain. In other words, an absolute maximum is the highest point on the entire graph. If it is higher, if the Y value is greater than any other Y value in the entire function, then that is an absolute maximum. Absolute minimum is the same idea, only it must be the lowest Y value for the entire graph. A local maximum is higher than any point nearby, and a local minimum is lower than any point nearby. Now, the absolute maximum and minimum are also considered local, but they're only considered absolute if they are the absolute highest or the absolute lowest. Look at this example. We're going to identify and classify the local extreme points of F first. So look at F and decide what the local extreme points are. We have two local minimums, the point AB and the point EH, and one local maximum, which is the point CD. Now let's do the same for G. We have a local minimum at JK and a local maximum at MN. Now, describe the absolute extreme points for F and G. Okay, function F does have an absolute minimum value, and the value is h. Remember, whenever they ask for the value, they want the y coordinate. So the point of the absolute minimum is EH, the value is h. It does not have an absolute maximum because the graph on both sides goes way up beyond point CD. And graph G of X has no absolute extremes. The graph extends in both directions, far above and far below those two local minimum points. Let's talk a moment about hidden behavior. Looking at a graph here, I'll give you the equation. We've got x cubed minus 2x squared plus x minus 2, and it's in a standard 10 by 10 viewing window. Let's make a conjecture about possible hidden behavior and verify it. In other words, is it possible that this graph is doing more than what we can see here because of the viewing window? The graph seems to level off between 0 and 2. So that's a good place to check and see if it's maybe doing more than just leveling off. If we zoom in tightly to that, we may find that the behavior is a little more interesting. And so they changed the window. You could also use the zoom function on your calculator. I like zoom box because it lets you draw a box around what you want to look at more closely. But when you change the window or zoom in, you can see that it doesn't really level off. It actually rises and then falls. So we do have a local maximum and we do have a local minimum. Now granted, they're not a huge difference between the two, but there's definitely a higher point and a lower point. So the point of this is, no pun intended, be careful. Just because it looks one way, it might look different when you zoom in. So zooming in is always a good way to double check your graph. All right, so how many local extrema? Well, a linear function has a degree of 1 and has no local extreme. In other words, a line is not going to have a highest point and a lowest point, or a higher than the rest point and a lower than the rest point. A quadratic function has a degree 2, and as we've already seen, it has one extreme point, either a maximum or a minimum. And that extreme point will be an absolute maximum or minimum. Now, a cubic function has degree 3 with at most 2 local extrema. That does not mean it will have 2 local extrema, but the most that it can have is 2. A quartic function, degree 4, has at most 3. That doesn't mean it will have 3, but it will have no more than 3. In fact, in general, the number of extrema or turning points of the graph of a polynomial of degree n greater than 1, so if we have a degree greater than or equal to 1, the number of turning points is at most n minus 1, the degree minus 1. A linear function has degree 1. 1 minus 1 is 0. It has 0 extremes. Quadratic is degree 2. 2 minus 1 is 1. Cubic is degree 3. 3 minus 1 is 2. At most 2 extremes. A 10th degree equation at most can have 9 turning points. Now again, that's an at most. It doesn't mean it will have that many, but it cannot have more than that. End behavior. Okay, if the value of a is positive for the quadratic function, the graph opens upward. We've seen that before. If it's negative, it opens downward. The sign of a determines the end behavior of the graph. It determines whether the ends will go towards infinity, in other words, keep going up, or negative infinity, keep going down. In general, the end behavior of the graph of a polynomial is determined by the sign of the leading coefficient and the parity, the oddness or evenness of the degree. Here's a little bit of information about the end behavior. And I know this looks like a lot, but the diagrams on the right kind of help. It says, suppose that a times x to the nth power is the dominating term, that leading term of a polynomial function p of odd degree. So we're looking at the diagrams on the top. If a is greater than 0, if the number in front of that x with the highest power is greater than 0, then as x goes to infinity, as x values get bigger and bigger and bigger, the y values will get bigger and bigger and bigger. And as x goes to negative infinity, as the x values go further and further and further into the negatives, the y values will do the same. So the end behavior of the graph is of the type shown in figure 52, A, the first one, and we symbolize it with, you can see the little arrows. The arrow to the left is going down, to the right is going up. Now if A is negative, we're going to expect the opposite to happen. As x gets higher, y is going to get lower. And as x gets lower, y gets higher. So it kind of does the opposite thing there. That's for odd functions. That's when that highest power is odd. When the highest power is even, as the absolute value of x approaches infinity, as the absolute value of x gets bigger and bigger and bigger, then the y values are going to get bigger and bigger and bigger. And this is when a is positive. So the end behavior, both ends go towards infinity, and we use the little up arrows for that. When a is negative, as x gets bigger and bigger and bigger in either direction, y gets smaller and smaller and smaller as more negative. So the end behavior, we have it going down in both directions. It's important to remember with an even degree, both ends are going to go in the same direction. They're either both going to go up or both go down. With an odd degree, they're going to go in opposite directions. And if you can keep straight what a is telling you, it'll make this a whole lot easier. We already know it for the quadratic. Just extend that to the rest of the even degrees. For odd, when a is positive, it's going to go up to the right and down to the left. When a is negative, you just reverse that. See if you can match each function with its graph. Now don't graph these on your calculator. Use what you have already seen as far as graphs go. Use the information about how the graph is going to look when it's even or odd power and when that first term is positive or negative. Pause the recording, see if you can match them, and resume the recording to check your answer. Okay, you should have matched function f with graph C, function g with graph A, function h with graph B, and function k with graph D. Okay, so we're going to talk about the number of x-intercepts or real zeros of a polynomial function. The graph of a polynomial function of degree n will have, again, here's those two words, at most n x-intercepts or n real zeros. At most. It may not have that many, but it cannot have more. So for example, we got p of x equals x to the third plus 5x squared plus 5x minus 2. Based on this rule, I know that the most number of x-intercepts that I'm going to have will be 3 because I have x cubed as my highest power. when I graph it in a standard viewing window, I can see the x-intercepts, and I can use the calc function. I can go to second trace, which is the calc function for graphing on my calculator, and I can use the intercept function there, and I can find those three intercepts. When I do, I get -2, about -3.3, and then about 0.3. Again, if you need a little help seeing them, don't be afraid to zoom in and get a closer look. Okay, here we've got a polynomial, 5th degree. You can see it for yourself. We're going to state the domain, determine the range, use the graph to find approximations of local extrema, use the graph to find the approximate or exact x-intercepts. And before I reveal the solution, why don't you pause the recording, give it a try, resume the recording to check your answer. It's a polynomial, so the domain for any polynomial, unless they tell you otherwise, is all real numbers, so -infinity to infinity. The range, well, it's an odd degree. The evens are not going to be all real numbers, but odds will. So again, numbers. The extreme points, well, using our calculator, we have a local maximum point of -2.02 and 10.01. and a local minimum of 0.41, -4.24. Now they give you a little hint about what's coming up either second semester or next year, depending on whether you're a junior or senior. Looking ahead to calculus, the derivative gives the slope of f at any value in the domain. The slope at local extrema is 0 because the tangent line at this point is horizontal. And those are very important points when you do calculus. In part D, we're going to use the calculator to find the x-intercepts. Again, we're going to use the 0 function under calculate, and we get -1, which is exact, 1.14, and -2.52, and both of those will be approximate. Okay, we've talked about comprehensive graphs before, and we've said that they are the ones that show the most important features of a graph. And for a polynomial, it's going to be the intercepts, the extrema, the end behavior. Those are the most important features, and you need to have a graph that will show all of them. So all x-intercepts and the y-intercept, any extreme points, and enough of the graph to reveal the correct end behavior. So make sure we're seeing enough where we know there aren't any more turning points. The graph is going to continue going up or going down as it's doing in the window that we see. Okay, give this problem a try. We've got a viewing window that's -1.25, 1.25 for x, by -450 for y. Is this a comprehensive graph? Are we seeing everything we need to see? Pause the recording, think about it, resume the recording to check your answer. Okay, this is a 6-degree polynomial, which means that it can have 6 intercepts and it can have up to 5 turning points. It can have up to 6 intercepts and up to 5 turning points. So it's really worth seeing if there's some more to this graph. And when we widen out our x values, and they also widened up the y values so that we can see a little bit more here, we see that there was a lot that we were missing with that first window. We do have 1, 2, 3, 4, 5, 6 x-intercepts. We are seeing them all now. We know there can't be any more. Let's see, we've got 1, 2, 3, 4, 5 turning points. So this function actually has the most number of intercepts and turning points it can have. And since we have counted all those, we know there are no more. We can be very certain that we are seeing a comprehensive graph. Okay, one last example here. This is a curve fitting again. It says the monthly average high temperatures in Daytona Beach are shown in the table. In this table, the months have been given the standard numbering, so 1 is January, and so forth. Plot the data, determine a polynomial function to model the data. Use your function to determine the average high temperature in April and compare it with the value given in the table. So if you remember how to do this, we're going to be plotting the data and then see if we can fit a curve to it. Pause the recording, give it a try, and resume the recording to check your answer. Okay, here's our solution. First we plotted the data. You can see that in the graph that's below here at the bottom of the screen. And it's definitely not linear, so we know we don't want linear. Now it could be quadratic, so they try that first, and you can see with figure B, the quadratic model just doesn't quite fit it. It kind of sort of does, but not quite. So we're going to try something else. It's possible that it could be a 4th degree, because we see a little extra curvature going on there. So they tried the 4th degree. Now you can find this in the Stat Calc menu. It is quartic, Q-U-A-R-T, regression. And you can use your calculator to do that. You select that. Be sure the data has been put in list 1 and 2 first. And then when you do, you get this equation here. And you can see in figure C there where it was plotted with the data, and it actually fits quite well. If you go by the graph itself or by the equation, putting the numbers in, you get that it's about 80 degrees in April, and the given table of values agrees with that. Okay, the rest of these are some examples to try. Pause the recording, give them a try, resume the recording to check your answer. Do this till the end of the video.